Why are you videotaping yourself?
I'm videotaping the class.
But you're not really.
But I am.
But you're not. Because it's not videotaping the class itself. You're just listening to it.
Yeah.
But it's not videotaping the class. That's video recording.
I had 12 cups of coffee yesterday. Stop.
You know, sleep is a thing that, like,
I haven't put together my A-Rap poster yet.
So apparently you
I have
can't
no
come
free
up-
mod.
come
Dude, isn't that doing that?
Yes, it is.
Dude, don't worry.
No, do not encourage this.
I will encourage what I want.
Don't worry, my mom's already
You're the fifth person I've seen today who hasn't done that yet. I spent like 6 hours on that thing last night.
No, I don't believe in it.
Literally just use Wikipedia.
It's just funny.
I did.
I had to ask Dr. Don about this one, huh?
Yes.
We'll throw her in Einstein probably.
Actually, no, that would be the Drake equation. That was Drake, not Einstein. Although,
I think you have 7 guns. You want me to put that in the thing?
Sorry again, I only have approximate answers. Number 1 is 40 GeV.
40 what?
40 GeV. Number 2 is 2.65 GeV over C. Number 3 is 39.91 GeV over C squared. Number 4, 2 answers. One of them is 200 GeV over C. The other one is 29.98 GeV over C. I guess not quite 200, right? It's 199.997 GeV over C. It shouldn't round. That's momentum, right? Yeah, it shouldn't round. Number 5 is 170.01 GeV over C. Number 6 is 154.9 GeV over C squared. Number 7 is 154.9 GeV. Number 8, 2 answers, 77.45 GeV over C and negative 77.45 GeV over C. Number 9, 171 GeV over C squared. Number 10, 120 GeV over C squared. It's a good one, right? 120. Yes.
Well, we make educated
guess. You pick 2 numbers and add them together.
Yeah,
right?
yeah.
For the challenge, the mass was 55 GeV over C squared, and the speed is 0.6 c. 55. Okay. Questions on the homework? Okay. Mass, yeah. That was for the challenge. Mass is 55 GeV over C squared, and speed is 0.6 c. Okay, wait, you got 7?
Yeah, I got it.
Okay, then 8 is easy. Okay, wait. If you know 7, then for 8, all you have to do is take this, and the proton's mass is 1 GeV over C squared. I am saying all the units properly because you should. However, if you, like I said, if you leave off the C or the C squared, it's not the end of the world. Most of us do it. I might not even know this. Yeah.
Can you explain how to get to the 7?
Happy to. Okay. So 2 protons collide. So we'll have to work our way through this from the beginning, which is fine. And one is an energy of 200, one is an energy of 30. Okay. So you have 2 protons colliding, and the mass of a proton is about 1 GeV. That's actually true, by the way. It's 0.938. 1 is close enough. Especially when the energies are, what did I say, 230? Okay. The thing is, if you know the mass of the proton and you know the energy of the proton, what else can you find? The momentum of the proton, right? So that was number something, where you find the momentum of the 2 particles, right? You found those that are kind of funny numbers, right? But you can find those easily enough, right? Then, once you know those, that means you can find the total energy is going to be 230 GeV. The total momentum is going to be something, right? This is going to be P1 plus P2. Keeping in mind that one of those should be negative, right? Because these are colliding. So one of the momentum should be negative. It doesn't particularly matter which one. Then, once you have that, if you know the total energy and the total, now you go to collide and form a new particle. Okay? The collide and form a new particle. That particle will have an energy and momentum equal to the total energy and total momentum, right? So this particle will have this energy and this momentum will collide. Because, right, if they collide and form a new particle, that's the only particle in the system. So it must have all the energy and all the momentum. Okay? Good. Which means the mass of the new particle is going to be equal to, well, mass squared is going to be equal to E total squared minus P total squared. Okay? So those like the first three problems of this set, right? Like 4, 5, and 6, right? Is to get through those. Those are energy momentum manipulations. You need to get used to them, right? Momentum is the only one that's a vector. That will need plus or minus signs. Energy and mass are always positive. But the momentum is easy to forget that, so watch out for the plus minus signs of momentum. And then you have those, and you can just add them together like nothing. It's really easy, right? It's nice, straightforward, simple, and then you can use E squared minus P squared equals M squared over and over and over, right? Already we've used it 3 times. Once to get the momentum here, once to get the momentum here, then after we add it, we use it again to get the mass, right? And we'll keep using it. So, the only thing to watch out for is that these all have to apply to the same particle, right? In the same reference frame, right? So, E in a given reference frame for a given particle, and P for the same particle in the same reference frame, right? But mass, of course, is invariant. So that's the same in any reference. And that's the key here. So this first part you want to make sure you do. This is just adding energy and momentum together and using E squared minus P squared equals M squared over and over. That's all you do. That's all you do, and it works great. But then the next questions are about another reference frame, right? 7 and 8 are asking you about what about the center of mass reference frame. Okay, so at that point we can use invariance to make everything good. Because I have one invariant quantity written on the board. Which one is that? The mass, right? This calculated mass, which if I recall comes out to about what, 170 is what I said?
154.
Okay, so no. Okay, 154.
170 was the total momentum.
Oh, that was the other one. Yeah, that's right. Okay, so 154.9 GeV. Well, sorry, that's actually mass equals that, right? Notice I just say GeV for mass because C equals 1 and then that, you know. Then this number is a number that's the same in every reference frame. Okay? So we know that E in the Earth's reference frame squared minus P squared in the Earth's reference frame equals M squared. But since mass is invariant, what's also true is that E in the center of mass reference frame squared minus P in the center of mass reference frame squared also equals M squared. Since n is invariant, you can do this, and this allows you to basically change reference frames without having to do a Lorentz transformation, right? But just sort of pivot through the invariant quantity. So, since this is true, but in the center of mass, what's the total momentum? 0. So that means that this is 0, right? And so 0. So that means the E squared, the center mass. Energy squared in the center of mass is equal to the mass squared in the center of mass. That's to say, the energy in the center of mass system of this new particle is equal to its mass. That actually makes sense. You could have got that independently, just from the fact that in the center of mass reference frame, what's the particle doing? It has to be, it's the only particle, the total momentum must be 0, so it must be stationary, so its energy must be equal to its mass, right? So, so that's normal anyway. But this trick works for any reference frame, right? You can transform to another reference frame by just E squared minus B squared equals 1n squared, E squared minus B squared equals another n squared, and then you can find your way to another reference frame. Works great when energy and momentum are what you're dealing with. You can do this all the time, and it works great. You can actually use that to do some of those problems like 9 and 10 on that earlier homework with the balls hitting each other and stuff. You can use this method to avoid Lorentz transformations.
So then, so you get like 154, like the same mass.
You get the same number.
You plug it into that.
And then to find the energy, you plug that number you get into here to find what the momentum would have to be.
So then, like, so those two individual momentums don't.
1, 2, 3, 0.
Oh, okay. So let me look at number 9. Sorry, I realized.
Number 2
okay.
is 2.65
I
G. If you ever see
yeah, I
it.
haven't finished doing this yet. Okay. So in the center of mass frame, you have two protons.
G is
going like this.
39.9.
That collide form a single thing. Sorry, this frame is moving. In this frame it's not.
39.9.
Right? In the center of mass frame, this is what happens. Okay, good. Yeah, I'm not done yet. So I found that the energy of this thing is equal to 154.9 GeV. Right? Now, if I want to know the energy of the protons in the center of mass frame, this is good because they're protons, which means they have the same mass. Okay? The protons have the same mass. Well, if the mass is the same and the momenta are the same or equal and opposite, right? Because they're the center of mass frame, so they're meant to have to cancel out. So their mass is the same and their momentum is the same. What does that mean? Their energy also has to be the same. So they have as each other, right? So they have to have the same energy, same momentum, and same mass. So therefore, I can easily split this in half, right? So this is 154.9 divided by 2 is the energy of this proton, right? Which obviously you can do, right? That's 77.45. GeV, right? And it's the same over here. Yeah.
So how would you do that?
But a great question. What would you do? So that one, and this happens all the time, where you get two things that are the same mass. From the same mass, the center of mass frame is extra easy to work in, especially when the particles have the same mass, because they have to have the same momentum. And if they also have the same mass, their energy is the same, and it all splits in half. If it doesn't, what you have to do is a system of equations, okay? And it's not actually that bad, but if they have different masses, then you still, as long as you know what the masses are, then you still can say, you know that basically E1 plus E2 equals the total energy, total, and that P1 is equal to negative P2, so the masses are the same, and you know what their masses are. And then you can just use, and then you also basically have E1 squared minus P1 squared equals M1 squared, P2 squared minus P2 squared equals M2 squared. Now technically this is 4 equations with 4 variables, but like really it's very easy to solve because so many of these solve very fast, right? So therefore you could use that to solve what they were in general, if you do the analysis with you. Okay. This homework is important. I want you to understand it. If for whatever reason you didn't really get to it, like that's fine. But you need to go back to this. It's really important homework. Okay? Yeah.
0 or 9 is
Sure.
similar to
No, they're actually more different than you might think, but they go together. Oh no, sorry, I was confusing with a different problem. Okay.
229.8. He also did one.
Okay. Right. So a particle is going along.
I got 2.65 G.
Right?
Okay.
It decays into 2 other particles. So this is a very important thing. Into a Z and W boson. Okay, and the question is, now I don't tell you anything about the Z and W boson, except the mass, right? The question is, what is the minimum mass of this particle? Okay? When it says minimum, I mean there are a lot of possible things that this thing could have, right? But it wants to know what's the minimum for this to be possible. Why is there a minimum? Why is there a minimum mass at all? Well, yeah, because mass is a form of energy. So conservation of energy means since there is energy in this final state, you must account for that energy in the initial state. Now you might have said, oh, well, there's 600 GeV in the final state, which is way more than the masses of these guys. I mean, the initial, right, 600 GeV of energy, it says, right? Which is way more than the mass of these guys, so it should be no problem, right? But we have to make sure that this stuff has to work in every reference frame. The mass, of course, is a variant, right? So, in which reference frame do we kind of get the minimum energy for this particle? Hang on, let me go ahead. The center of mass frame, good. Because the center of mass frame, what is this particle doing? It's staying still, right? So if we switch to the center of mass frame, it's just a particle staying still that then blows up into a Z and a W. The numbers of the particles I give you are actually mostly real. I round off the numbers a little bit, but they're basically real numbers. So this is like real stuff. This is like actually touching like real physics now. And so it's kind of exciting, right? So so when this happens, let's say this particle has a mass m, right? In this reference frame, its energy we know is 600 GeV. In this reference frame, compared to the other thing, it will be higher or lower? Lower, because remember, when you're moving, your energy always goes up, right? So your minimum energy is always when you're at rest, when that's equal to your mass. Okay, good. So here, what's the energy of the particle going to be? M, right? Good. Now, what's the minimum energy that the Z could have in this frame? Yeah. Yeah, the minimum amount of energy it could have would be its mass, right? That basically means it's at rest. Now, would it ever actually create just one of them completely at rest? I mean, probably not, but that's sort of the limit, right? It'd be going very slowly. So the minimum energy of this would be 91 GeV. The minimum energy of the W would be 80. So in sort of the worst case, in the minimum energy case, that's how much energy you have here, right? And so therefore, what would n have to be for this to work? The minimum value of n is 171. So n has to be greater than or equal to 171 GeV. Okay. So this minimum case question, right? What I did was you look at it in the case where there's minimum possible energy. Minimum possible energy is always when you're not moving. And since I didn't totally tell you anything about the Z and W, they could be not moving in this frame. You switch to the center, so this number of course is useless, you don't use it. You switch to this reference frame because this is the minimum energy reference frame for this particle. And the mass is invariant, so here. Now, if you actually work through everything with momentum and stuff like that, you'll discover that that's actually true in this frame as well, but that's irrelevant. It's so much easier to work with the center mass reference frame, and mass is invariant. So once again, this is part of the usefulness of invariance. You can answer questions about mass by choosing your favorite reference. Yeah?
Do we need to know how to work it out in like the reference?
It'd be kind of a good exercise. It's not hard. It's just energy and momentum calculations, right? You know, we can find the momentum of this in terms of its mass. And you can use conservation of energy and momentum to find out energy and momentum of these guys in terms of n, right, and their masses. And then you can solve and show you know what happens, and you'll discover that you'll still get this limitation on its mass. It's quite a bit of work, and it's not necessary work because you know the answer. On the other hand, it might be helpful for you to just be used to learn to think about energy and momentum. So it wouldn't be bad. Okay.
Do you think?
Okay.
Would you need any like relativistic things if you're doing it with momentum and energy?
Which relativistic things do you need?
I don't know, just like for the momentum, say all reference frames, or could you just say like the one reference frame?
For the one I was just telling John, yeah, that one is all of this reference frame. Yes, can you work it out all one reference frame? That requires no transformations or anything.
It's like regular.
I mean, kind of. You still want to be using e squared minus p squared equals m squared a lot. That was very relativistic. Yeah. Sorry. Oh wait, you had two things.
Would you need like angles?
You just assume it's one dimensional. Because there's no angles to speak of here, they have to come out back to back. So any angle would be trivial, I think, in this case. Oh wait, could I be wrong? Maybe I'm wrong. I might be wrong. Maybe you would need the angles to make the numbers work.
with the center of mass frame, so like the minimum possible energy is like, it's where like the Z boson and the W boson are also stationary and the particle is stationary, so like, then, like,
Yeah.
so is that like a realistic scenario?
Well, actually reaching that point is, I mean, the probability of that would approach 0, but it's the limit, right? It's the limiting case. It's the minimum possible, right? Really, of course, you would never get a particle exact. You don't get to control massive particles. We have no idea where massive particles come from. You definitely don't get to choose. So, like, you'd not be able to get to be that exact anyway. But what you can say is this, for example, that number I picked is not completely out of a hat. This is just barely below the mass of the top quark. So that means the top quark in principle could do this. Those other things would prevent it from doing this particular one. But a Higgs boson, which is a mass of 125, would not be able to do this. Okay. So you can make statements about what this particle could and could not be based off just this simple limit. In fact, we do that all the time in particle physics. And this particular question is a really important one. It comes up a lot. Okay, yeah.
For the statement that the minimum energy is the mass, that's when you're giving the mass, so then you can switch it, you're giving the energy and say the maximum mass.
Absolutely. Is that what number 10 does?
Yeah.
I think so. So I already call it. Let's take a look. Yes. So so number 10 is sort of what I'm going to say, sort of the reverse version of that. It's 2 photons with an energy of 60 GeV each. And it says what's the maximum mass? The maximum mass now that they could produce. And the answer is, well, you can actually do this calculation in any reference frame, right? Because the mass will never change. So, heck, why not this reference frame, right? And if you're just looking for the maximum, it's quite straightforward because you have a certain amount of energy here. How much energy do you have in the system? 120 GeV, right? Okay, that energy is going to go into 2 places, 2 forms. Some of it will be turned into mass, some of it will be kinetic, right? Okay, good. So the maximum mass situation is where the energy does what?
It equals mass.
It all goes into mass. So the maximum mass situation would be a stationary particle, which by the way, this is center of mass anyway, so that would happen anyway. So a stationary particle, which just energy equal to its mass, which is the sum of these 2 energies, so 120 GeV. Yeah.
Is there another way you could do this? Basically, like the energy and the mass of each thing is the same, so the momentum like absolutely equal, and so then total momentum is 0.
Yes, you can, that's the equivalent argument, right? That this basically, you realize that they have the same mass, they must have, and the same energy, they must have the same momentum, therefore this is the center of mass frame, total momentum is 0, therefore this thing is stationary anyway, right? That's another way to do that. Okay, but the key is also, this is very important, because very, very soon, as soon as we finish the test, we're going to start talking about colliders. And colliders collide things together, and you have to ask yourself, what kind of particles can you create? And the biggest limitation is energy. It's all about the energy.
Is it possible for the first question to ask what the maximum energy is and the second one be minimum?
No, because there is no sensible one. In this case, this particle could be 100 billion GeV, and it could decay to nothing stopping it, right? It's easy for a lot of energy to decay. Then these guys just have a heck of a lot of kinetic energy, right? Because why not, right? And this one, similarly, it's very easy for these protons to collide and create an electron, which is a mass of 0.0005 GeV. Like, sure, why not, right? Well, actually, in center mass frame, you wouldn't be able to. You'd have to have 2 particles. But anyway, like in principle, there's no minimum. That's not the problem, right? So when you have colliding particles like that, then the maximum is your real question. And when you have a single particle decaying, then the minimum is your limitation.
What about with like the you can't go faster than the replacement with that high?
That's built into the energy momentum definitions, and that's why we work with energy momentum. There's no limit on the numbers for energy momentum, right? Because they convert to extremely high sub-c velocities. So that's why energy. That's why when they talk about. We'll start talking about just next week. I'm excited. I love colliders. But they all, you know, if you guys have ever been to Fermi Lab or read any of their stuff, they're always like, we accelerate protons to 0.99999, you know, to 99.99997% the speed of light. And like, no one uses that. You just look at the energy, right? Like the question who cares, okay, they accelerate protons to 980 GeV. That's what we need to know. Yeah.
So you mentioned just now that in other reference rates, like the particle energy in the reference rate, it would be large enough theoretically that amount of energy we get from smaller particles. Could it ever happen? Or like in one reference frame, in the reference from the center of that, that's not possible.
It will never work in one. What happens in one reference frame stays. No. What happens in one reference frame happens in all reference frames. If it's kinematically forbidden, meaning it violates conservation of energy or momentum in one reference frame, that is also a problem in every reference frame. So like I said, if you work this one out in detail, and I don't think you need 2 dimensions, the more I think about it. But I'm not completely sure still, I haven't done it. But if you work this one out in detail, you will end up with the same limit, the exact same limit. Okay, because mass is invariant, so you have to. Okay. Good questions, very good questions. And some more to think about. Is there any other questions? Excellent. Okay, so we know we have a quiz coming up on Tuesday. This material is important stuff. So let me just tell you what's on the quiz. It's energy momentum.
I don't think we could have predicted that.
So in particular, don't worry about the older stuff. Velocity transformations, Lorentz transformations, time dilation, stuff like that. It's not going to be on there. And in fact, you don't even really need to do Lorentz transformations because you can use invariance to get around them, right? So you don't even need to particularly worry about that because most of the time you can use invariance. The one thing, so you've learned all the material that is needed. Today we're going to cover a very important technique for doing columns that are relevant. I started it last time, didn't get very far, so let's do it for real today. What we're doing today, I call them 4-vector problems, and it's an incredibly powerful and essential way of doing certain types of problems. But you have to, so you have to learn it. It's not that hard, but it's kind of a lot of steps, so it takes practice to be able to go through all the steps. That's really what it is. It's more about practice than difficulty. It's not that hard, but if you don't practice it, you might forget how things go. Okay? I have done my best to try and give you sufficient practice for this. And in fact, in the spirit of that, dang it. Hang on, sorry, just a second. Okay. I'm going to give you a standard problem that's what I call this 4-vector problem type. Okay. This is one where you cannot do things quite so simply. Okay, here we go. Okay, let's say let's put some definite numbers on it. I think people work better with numbers than letters, so let's do some numbers, okay? We have 2 protons. These are protons. Symbol for proton is P. The energy of the proton is 1,000 GeV, each of them. This is basically a rounded version of a Tevatron interaction. Tevatron's the machine at Fermi Lab that's now shut down because the LHC took over. That's kind of a cool name, huh? Tevatron. So-called because its energy is 1,000 TeV, which is also 1,000 GeV, which is 1 TeV. So TeV, TeV, they call it Tevatron. It's the first machine to ever reach that energy. So you have these protons, they're colliding, okay? They collide, and they become a top quark and a bottom quark.
What?
Top quark. Perfectly reasonable. Plenty of energy to do it. And which is the question?
You're wrong.
Okay.
You're very wrong.
So I'll give you some masses.
All the time.
Mass of the protons are, well, okay, so important note. Every particle type has a unique mass. So when I say the mass of the proton is 1 GeV, that's rounded, that means the mass of every proton is 1 GeV. There's never any, if it doesn't have that mass, then it's not a proton. Okay, so you once you see it for a particle, that's true for all the particles. And then the mass of the top quark is about 175 GeV, and the mass of the bottom quark is about 5 GeV. And if you're curious about where those numbers come from, you'll have to keep wondering, because we have no idea. You'll have to check with God. Now the question is, what is the bottom quark's energy, so the B's energy, in the top quark's reference frame? So what is the bottom quark's energy in the top quark's reference frame? Okay, so basically what I have is, this is given here, as you can see, in the center of mass reference frame, because these two protons have equal and opposite momentum, right? But the question I'm asking is about what happened in the top reference frame. Now, do we know the velocity of the top relative to the center of mass? We do not, right? Do we know the velocity of the bottom? No. Do we know the velocity of anything? No. But to do a Lorentz transformation, you need to have a velocity, right? Do we have any other information to do the Lorentz transformation? Well, not really. So this is where I said you have to set up an equation doing conservation of energy and conservation of momentum, but with the Lorentz transformation of both of them together. So basically, energy in here has to equal Lorentz transform version of energy here. Momentum here has to equal Lorentz transformation version of energy and momentum here. And then where's the third equation? You need a third equation. Oh no, you have that information, right? And then you have to solve for phi and for energy simultaneously. But solving for phi is bad because they've got those gamma terms in there, right? So horribly, horribly messy. So we're not doing it. Yeah.
So then we can write 4 vectors for each of them and then do.
So let's let me work through it real carefully. Actually, I'm gonna have you work through it. Okay. We're going to name these 4 vectors. Let's start with these guys. This one will be called, we will label 4 vector T and 4 vector B. I think we can figure this out, right? All right, I want you guys now to write down what is the 4 vector for the top quark, what's the 4 vector for the bottom quark. The only one that you fill in is, the question is, what's the B quark's energy in the top reference frame? So, first of all, what reference frame are we in? The top quark's reference frame. So we're in the top reference frame. And secondly, we don't know the energy, so obviously you can't fill that in, so we'll just call that E. Okay, so that's one variable you can write in terms of E. Okay? Everything else you have enough information to do. So try and fill in these 4 vectors. Remember, the last 2 are always 0 in this class, right? So go ahead, fill in. You can talk to each other and stuff.
Alright, so we know that the top quark is, if we're in the top quark's reference frame, and the top quark is not moving, which means that its energy is equal to its mass. So its energy is 175 GeV.
It's equal to the mass.
And if you know that, then you can find the momentum in the top
Because we have its mass.
0. Wait, then why can't?
So its momentum 0 because it's not moving.
Yeah.
Yeah. Momentum equals 0.
We have the mass for that.
And we can't find B's momentum. If we knew B's momentum, we could find its energy.
Well, we can find its momentum because we have its. We know.
Good start.
Oh, that was a little scary.
I'm breaking now.
Yeah. What?
You said good stuff.
Oh.
We're on the right track.
Oh, okay, but he like looked at you, he's like, eh?
He said, and just walked away.
Oh, okay. Alright, so for the top quarks, we have the top's 4 vectors, so we know. Wait, hold on.
We can do the A times B thing, can't we?
That's what I was thinking. We can do A times B with this information.
Yeah, okay, I've got it.
Wait a second, no, never mind, we can find the momentum.
Of the bounding quarks?
No, of the,
because we have their energy and their mass.
Yeah. So then we can do, in the center of
It's like
mass
everyone's in
frame.
the same spot.
Yeah. Oh, that's how we do
Here,
it.
what do you want to label the two protons, A and B?
That's the mass, right? Energy will be the same as mass sometimes, so there's no reason to say
What should
momentum.
we label these?
Oh wait, yeah, that's
Let's just make it
P1, P2.
P1, P2.
Guys,
Yeah.
you're all stuck in the same spot. Remember, when in doubt, what do you use?
People.
The internet.
When in doubt, which equation do you use? Okay, well then.
Okay.
I don't want to use people.
So we know that P1
You
equals
can write in terms of E, by the way.
P2 equals.
Alright.
So then,
We'll write in terms of E.
momentum equals,
We can use inner product to solve this. We can use inner product to solve this.
Alright, so we know that one of their momentums is equal to,
AB equals AB.
okay. So first off, what's 1,000 squared? 1,000 squared is 100,000, right?
yeah,
No, it's 1 million. It's 1,000 squared.
Oh, you're right.
1,000 squared is 1 million. It's square root of 999.
So here, let me fill these in for
Yeah,
you.
plus on the top, minus on the
the one that's going to the
You guys
left.
pay attention from it. Sounds like you have moved on for a bit, but let me pull you together for a moment. So we got that this is 175. You know, let's be honest. We all leave off units once we start working on these, right? So we'll put them back on in the end. So this is 175 and 0. And that decision was really important, right? When you're in one particle's reference frame, then you know one of the four vectors already, right? The energy is equal to mass, the momentum is 0. You can only do that for one of the particles, right? And if you're in that particle's reference frame, you can do that real fast. So that's a real important one. We'll use that a lot. Make sure you have that ready. Then, for the bottom quark's reference frame, you don't know anything about it, that's moving. But you already have a given energy and you know its mass, so you can use E squared minus P squared equals M squared to find it in terms of E. Like so. Right? There's no further simplification that is possible here. Okay. It sounds like you've already started on this, so go ahead and write the P1 and P2 four vectors. What reference frame are those going to be in? Center mass frame, right? Which is the same as the Earth's frame in this case, right? So go ahead and write what will those be in the center mass frame. Use E squared minus B squared equals M squared. You should have no problem filling this one out. So go ahead.
So now we end up with 1,000 squared minus 1. Minus 1?
Square root of that. It's just square root of 990.
He was lifting the 4 vectors.
Yeah, I'm ready. No. I have the 4 vectors written out. Now I'm starting into the dot product.
Oh, you're doing the dot product?
Dot product, which is
Okay.
1
Find the
equals.
dot product of, wait, okay. So you find the dot product of these two, then you can get,
Yeah, you can. What's 1 million? What's 1 million? 1 million. This. What do these multiply equal to? They multiply to 999.
You're given some pretty good information.
What?
No, they will multiply in the negative. Well, but it'll be plus that.
It'll be plus.
minus,
No, it's easier than that.
yeah, minus a negative 999.
Isn't this already in the center of mass reference?
So then we're going to get
So
Wait,
wait.
1
isn't all of
million
this already in the center of mass reference?
Is that the total?
So wait, we end up with, yeah.
No, that's the dot product.
All these numbers aren't they in the
Dot
center
product
of
of an
mass
energy
reference?
multiplier.
Oh, that's where
it
gives itself.
I'm pretty sure this is. But this
Yeah. When you dot product.
This is in the
Well,
center
that
of mass
has to
reference,
equal the
isn't?
top.
I don't.
The top one's reference.
I haven't slept for 3 days, dude. I would quit.
That has
What
to
about
equal
you?
the top particle and the bottom particle dot product, right?
The energy of B is going to be equal to that over 175.
What?
Okay, what'd you do?
How?
All right, so I have.
not listen to us.
No, you're talking whispering to yourself.
I said to us.
We end up with we do that. So here are four vectors, right? So for the top, the dot product is going to end up being equal to 1,999,999, right?
How do you know?
How do I know that?
The dot product is always is invariant, so that
No, I know, but like, okay, so fine, you multiply.
Correlate to the same thing though?
Yeah,
they always do.
yeah. So you multiply these, and then you multiply these. You get 1,000 minus negative 999,999.
1 million. 1 million minus negative.
Yeah, so you end up with 1 million. But then you go ahead and you multiply out this, and you find the dot product of this, which is going to be 175e minus 0. So this cancels.
Okay.
So you end up with just equals 175e. So then you can divide by 175 to get
All right,
the
ladies and
e for
gentlemen,
b,
may I get attention, please?
and then you can plug that in.
Then call you guys back here. I want to do this one working with you together, then I will give you time to work on more stuff with you yourselves, okay? I have practice problems, plenty of them. Yay. So, let's, but for example, these energies you can fill in because I gave them to you. And they were in that reference frame, so you're good. You know their mass, the momenta, will be equal to, 1,000 squared root of 1,000 squared minus 1. Except there is one thing you have to remember here. One that has to be negative. They're heading at each other, right? That's fine. You technically have two roots here, right, when you do that. So one that needs to be negative, one that is a minus sign. Okay, good. So here's the argument of what to do now. These represent the energy and momentum of everything in the system at different points in time, right? Therefore, T plus B is the total energy and momentum, right? And P1 plus P2 is also total energy and momentum, okay? And what do we know about the total energy and momentum? It's conserved. But there's a problem here, right? We can't set them equal to each other because why? They're in different reference frames. So therefore, even though they represent the same, even though they represent conserved quantities, the fact, that's not really what I meant to say. Different reference frames, I meant to say. Because they're different reference frames, they don't represent the same, they're not going to be the same values, right? Even though they're conserved quantities, T plus B is not equal to P1 plus P2. However, what does happen is that, and here's where we use our variance grid. We did this last time. What did we do? That's right. If we square both of these, right, then you end up with a quantity, T plus B quantity squared, or P1 plus 2 quantity squared. This quantity is conserved because it's constructed from energy momentum, it's conserved quantities, and it's invariant because it's a 4 vector. So you have a quantity that is both conserved and invariant. Okay? Therefore, these two become equal. As a quick side note, the name for this thing, the total, when you take the total energy momentum 4 vector and square it, you get something that the name of this is called invariant mass. That's the name for it, invariant mass. It's not actually the mass of a particular particle, okay? But it forms a value that is mass-like. It sort of behaves like mass. So it's a mass-like quantity that we can work with. Okay, so let's actually work this out. Now, when I work this out, I have a preference for how to do it. That I think is on the whole faster than other ones, although there's different ways. So while you could add them together, it's actually not that hard. There's a way I prefer to do it, which is to expand it binomially. Okay, like this: t squared plus 2t dot b plus b squared. Notice that's an inner product here, of course, right? And on the other side, p1 squared plus 2 p1 dot b2 plus b2 squared. Okay, just binomial expansion.
Let's see if I get this thing.
Wait, why don't you take the square root of both sides?
Why bother?
What?
Why bother? I mean, it's still true, right? But it's true either way. There's no square roots are messy. keep in mind, t plus b is not a scalar quantity. This has to be a scalar quantity, right? So the reason I do this is because it actually cuts out some of the squaring work. Although if you're sharp at your math, you'll realize sometimes it's better to add them first and sometimes it's not. And you're welcome to take advantage of this if you need to, but I think this is a good default. The reason is this. Whenever you have an energy momentum 4 vector squared, do you remember that? If you have an energy momentum 4 vector, you know, that looks like this, or we'll call it A, then what was A squared equal to? It's always equal to m squared, right? The square of any 4 vector is always equal to, of an energy momentum 4 vector is equal to the mass squared. And so you always have masses to work with, so it's easy. So this one becomes 175 squared plus 2 times, okay. Now this one we actually have to work out. So I look at the 4 vectors. This times this, the energy term gives me 175 times E. Okay.
I think it's
minus this times this, which gives me 0. Oh, happy day. And then over here, E squared is going to be equal to the mass of the bottom fork squared, right? So the 5 squared for a moment. Over on this side, the P1 squared will give me the mass of the proton squared, which is 1, plus 2 times P1 dot P2. Okay. P1 dot P2, so the multiplied of the energies will be 1,000 squared, 1,000 squared, minus the product of the momentum. If I take the product of the momentum, what am I going to get?
9.
Well, it'll cancel out the square root, right? It'll cancel out the square root, and there's a minus sign. Right? There's a minus sign. I already have a minus sign. That'll make it a plus sign. So, and then we'll have 1,000 squared minus 1. And then finally, so P2 squared is plus 1. Now notice what we have here. Look at this equation. How many variables are there? 1. Everything else is a number. And at this point, all you do is solve for E, right? Which is particularly easy at this point, right? In fact, a few things cancel out if you work with it. But actually, rather than work this out to the end, because I think you know how to do basic algebra, and this is very basic algebra, then I'd rather have you do some more practice yourself. Okay, so but let me explain what happened. Here's what we do. We can't, to make this work, we write out the 4 vectors. So you write out the 4 vectors in 2 different reference frames. Okay, because you're given information in 2 different reference frames. Put in an unknown variable. There you always have to have an unknown in there somewhere. Okay? Then you write out your 4 vectors in terms of that unknown variable. And then you can take the sum of the 4 vectors and square them, right? And set those equal. Because the sum of the 4 vectors squared is called the invariant mass. It's the same no matter what. It is both conserved and invariant. And thus allows you to, and then you set those equal, and you'll end up with a simple algebraic equation. You may have quadratic equations sometimes, but you'll never have a system of equations, which is what you have the other way. You'll never have, and you wouldn't have any square roots in it generally. Well, you might end up with them somewhere. I guess it's possible. Okay, so that's the general approach. It's not hard, but it is a bunch of steps. Okay, so it really just takes practice to get used to the steps, and then you can solve the problems easily. So let me tell you what I got for you. Up on Moodle, under the section called Practice, I have some practice problems. Oh, never mind. Okay, I have this practice problem, but we already did it. The one I'm looking for is where's that other practice problem? Oh, okay. So I have a few things. I have a PowerPoint that walks through how to do it. I have a problem that has a video. I know I need to get those videos working again. I need to talk to ITMC about that. They do work if you open them with VLC video player, which is free. Or you can just work, but the problem itself is there, so you can work on the problem there. And then you have your homework, which I'll go to. What I would like to do is right now, if you look at the one that says 4 vectors video problem, this actually works it out. This actually works it out in detailed steps, which is good. Okay? So that's good. So that's what I would like you to work on right now to see if you can get it to solve the problem. Now, that one has like 7 steps where it's split up for you, so like walk you through it. Okay? On the quiz, there's no subpoints. You have to do the whole thing yourself. So that's why I say need practice, so you understand what do I have to do in order, so I can get from here to there. Okay? All right, so why don't you work on that right now and see if you can see if we can get it.
Oh my god.
Yeah.
Hey. Oh, it's
No, because you're actually subtracting the quantity negative of minus 1. So you're subtracting a negative number. But this is a minus sign here, right? The product of these two is negative. Right? Right? Because there's a minus sign here and not here. So the product of these is negative. Then you're subtracting a negative number, so it becomes plus.
Or negative 1.
The minus 1 stays because it's negative times the quantity of this, right?
Initial state. Boson. Particles. Photons. Here's a reference frame for initial state. Would be final state.
Where's the correctness point?
The unknown particles.
Yeah, is it oh, it's pretty correctness too?
There's a telephone.
No, it's it says 4 vectors back to video problem.
Oh, okay.
These guys are just massive. That's why I do it that way, because it can simplify the math. And you can basically
Normal means unknown.
you don't have to math, you have
The final, no, initial is the unknown
that
W,
usually
right?
makes
The one
sense.
that's right.
Initial would be the unknown particle, and the last one would be in the boson's reference frame, yeah.
This one is simpler than this way, it's actually faster.
Wait,
Photons have
yeah.
mass.
But this one actually is faster than that first.
Not photons. Photons don't have mass.
Yeah, photons have
Yeah, I was wondering that when he had the photon had 1 GeV of mass.
Proton.
Why don't you ask him?
I already said
Oh, they're photons. Those are protons. Oh, I thought he said photon.
God damn, why is it proton and photon? Why is that a thing?
Because it's like photon and photon.
Shut up.
Write 4 vectors of the initial state particles in the chosen reference frame. I don't want to. I'm going to set this on your stuff.
here, I just wanted
I agree with that. Like 100%. But then I go, no, that it's not actually going to be over because I have all this homework stuff to do. I'm running that.
If you have energy and mass, if you have energy and mass, you can find the emergent, right? I know the. Why did I ask that question? I clearly know the answer. I don't know. Yeah. So we're starting with the. So should we work it out in the unknown particle and the W bosons first? This is relatively simple. See the last part of the equation for that one, the t squared plus 2tb then. Oh yeah. Yeah, you can just use that to help. Well, I know.
So you want to do is get it and convert it on YouTube. So I can also send it to that's the thing. So
Use the unknown particles reference frame for the beginning. So
yeah, right. So
and then the W for the other one. So the W boson at that point. I know, but no. Look at it. The photons have energies 60 and 120 in the W boson's reference frame. I know, but so it's still around.
actually halfway done. I like collected the files and I wrote them something. Oh, you know what? While I'm talking to you, why that actually
So do we know the unknown particles?
No.
So we can put that in as E.
Yeah. Basically, what we're trying to do is find unknown particle reference frame, the unknown particle to a vector square. That's what we're trying to find.
All right. So here's what we have. We know. So if we have the mass of the boson and we have the momentum in the unknowns. So we can
We can find the energy.
So 60 squared.
Wait a minute.
Minus 80 squared.
That's a popular 36 triangle.
345.
Yep. So it's
So
100
squared.
So the energy is 100.
Ladies and gentlemen, it is time to go. Sorry. These problems are very important. Please continue to work on them. Understand them as well as you can. I'll have homework up shortly as well. And you can do it.
This, that, oh, this one.
You're taking this. Choose a reference frame or you're given no